In general, one has to be careful. There are uncertainties in these models because people can misuse this out of context. Nonetheless, obviously, because there are not enough data to formulate some of the aspects of these models that we will look at, and because we don't have process understanding in some cases, again because of data. Remember, we collect data, we analyze them, and we make a hypothesis. We collect more data to test the hypothesis and make a theory, and we need more data to test the theory. So unless you have those kinds of data at sufficient resolution in space and time, and in the form that they are needed, like rates versus values, like temperature versus temperature change or warming rate, and for biological systems, pools of carbon dioxide and the flux of carbon dioxide and so on. They're not even easy to measure in the open system like the ocean or the atmosphere, in the soil, etc. So this is another schematic of the difference between a climate model and an Earth system model from this Scott Bonin and Doney paper, which is a very nice paper on the Earth system models and the need for biological predictions. So there is biosphere atmosphere exchanges in the climate model, and there is energy and momentum fluxes. Given the solar input, the physical climate is done, including hydrology. So in general, the biosphere is prescribed here typically as just observed leaf area index or some simple type of vegetation distribution and so on. Whereas we want to do Earth system models, then you want to have more details like smoke, dust, biogenic volatile organic carbons, agriculture, deforestation, permafrost, and so on that we talked about before. And of course, the ocean atmosphere exchange has to also be accompanied by the details of the ocean biogeochemistry and ecosystem. Could be like this, what is called a lower trophic level model with some representation of phytoplankton classes, could be functional types, could be size classes and so on, which carry the biogeochemical cycles with them. And typically they are either done by taking explicit carbon to nitrogen ratios, or just done with nitrogen currency but converted to carbon using stoichiometric ratios of carbon to nitrogen and so on. And the models have representations of iron limitation, silica limitation, grazing processes, sinking out by biological export. So they have the solubility pump and the biological pump and so on. But in general, there are three principal sources of uncertainty in climate predictions, which are as follows: those which arise owing to known future emissions of greenhouse gases, unknown future emissions of greenhouse gases and other forcing agents related to both human activities and natural variability. Could be volcanic eruptions that we don't know about, and other clathrate perturbation, let's say due to earthquakes or something, landslides. Those due to internally generated chaotic fluctuation in the system, for example, the phase of the El Nino at some point many decades in the future. So El Nino is a natural variability mode that happens in the Pacific. There are similar modes in the Atlantic and Indian Oceans, but El Nino has global perturbations and can trigger off feedbacks, as we saw with teleconnections, on forest fires, dust storms, marine ecosystems, carbon cycle, and so on. But and we also said during El Nino there is a mini global warming because the ocean is releasing heat. These cannot be captured exactly in a climate model. That's not predicting, but just simulating the future with some assumptions on the scenarios of emissions and other impacts of human activities. And then there are uncertainties due to simplifying assumptions made in building the climate. In particular, the representation of some sub-grid scale physical processes. So sub-grid scale is what I mentioned when I said depending on the grid size, the clouds are much smaller than the grid. For example, snow is only falling in part of the grid, or the land-ocean interface is a kind of a process that's not fully captured by having land and ocean separately represented, and so on. One can look at the uncertainties also as internal variability, model uncertainty, and scenario uncertainty. So this is again from the Bonin and Tony paper, and this is talking about the percentage of total variance attributed to internal variability, which is essentially natural variability, no external forcing, no human impact, no volcanic eruptions, etc. And you can see that as you go into the future, the model uncertainty begins to be smaller compared to the scenario uncertainties, the assumptions made in the impacts of human activities on marine ecosystem and carbon cycle. So essentially you are perturbing the Earth's climate system and Earth system, and ocean is responding and feeding back to the perturbations. So in the beginning, shorter term, let's say 2030, 2040, model uncertainty is huge and the scenario uncertainty is small, and internal variability, the natural variability, is well captured by the model, and that remains the same even on land. But on land, the scenario uncertainty is not that large because it's a fixed area. You are prescribing, let's say, agricultural land conversion, urbanization, deforestation, whereas the ocean is deep and it's vast, covers so much of the earth. So the uncertainty in the ocean scenarios is argued to be very large in this case. So we will come back to this idea of the internal variability, model uncertainty, and scenario uncertainty later on again in the context of projections. But in general, when you want to evaluate models and constrain them, you are going to rely on data, which comes with its own uncertainty, and sometimes there is just not enough data. For example, if you want to go back to the beginning of the Industrial Revolution, and we've been looking at various temperatures and so on, the coverage of temperature data, even surface data, let alone deeper ocean, becomes less and less in terms of the areas covered around the Earth. So that's going to become a problem. So it's not just uncertainty in the data collected in the past, for example, but also just not having enough data. That's going to create in the real world process uncertainty in terms of, let's say, interpreting exactly why the Little Ice Age ended. Was it because of the pollution, coal burning, and pollution on the snow and glaciers, or was it some other process? Was it the solar forcing? So those have to be interpreted by using combination of model and data. And in the Earth system, there are structural or parameter uncertainties. We will see some of those parameters. Basically, these are processes like the subgrid scale processes of cloud formation, or even precipitation conversion from clouds into rain, graupel, hail kind of transformations, and model dependencies. Just like if you drive different cars, you may get a different sense. Each model has a slightly different formulation of these non-fundamental principles. For example, the equations of motion, momentum, energy are kind of fixed, but the parameters you use in the models can make the results model dependent. And so you want to evaluate the model and constrain by considering those things: data-based constraint, data and model-based constraints. So this is kind of a heuristic way of showing what this means. But looking more specifically, this is from the NCARS Comet program, UCARS Comet program. It's showing a list of 20 climate processes and properties that typically need to be parameterized within the global climate models. So they go from solar radiation, because we are not completely sure of the physics of the sun. We can obviously foresee the 11-year sunspot cycle, but you cannot say how many sunspots there will be, so how the flux perturbation will be, how large will it be. Remember, if there are fewer sunspots, the radiation goes down. If there are more sunspots, the sun's output goes up, and this perturbation can be significant, and we don't always know how to do that. So solar physics models are used there. Scattering by aerosols and molecules, very difficult to represent explicitly and prognostically. And here even observations are seriously lacking, especially far away from land. Absorption by the atmosphere, reflection, absorption by the clouds, condensation processes, turbulence, reflection and absorptions at Earth's surface, so the albedo processes, topographies, so model topography is typically affected by the resolution of the model. So many times people do regional models for regional downscaling because they are regional. They can be run at higher resolution than the global models, so they can be used to represent the topography better, and also some regional climate, regional land use better, forest versus agriculture versus dry land, urban areas, and so on. In a global model, when you have coarse resolution, you will be obviously missing the subgrid scale details of land use as well. Evaporation, vegetation, deep convection, this is a key sticking point as well in terms of the parameterizations developed from observations that are very limited and missing a very basic process understanding, and so on. Okay, so those obviously are parametric uncertainties. As an example, I included this from Oak Ridge National Laboratory, showing details of a marine ecosystem model. I won't go through everything, but again highlight that we talked about size classes of phytoplankton, size classes of zooplankton which graze on them, resulting in detritus sinking particles, how they are decomposed, consumed, and returned as preformed nutrients to be brought back up by the circulation. There are land contributions in terms of pathogens, pollutants, nutrients, and there are fisheries represented in many models now, so they are not just lower trophic level models, but also include some upper trophic levels, etc. So there is the physical cycling or the solubility pump, and there is the biological pump, and there is biogeochemistry and carbon and iron cycle and so on. And it's critical to capture the rates of burial or carbon that gets sequestered into the bottom, including sometimes the benthic zone processes and reactive sediments and benthic fluxes of nitrogen, phosphorus, iron, and silica, and so on. So the difficulty here is there are again many parameters involved here, like growth rates, predation rates, grazing rates, rates of sinking, rates of decomposition, etc. So measuring the rates in the ocean is of course very difficult, and taking lab estimates into the models is very difficult as well. Plus, if the data is collected in the Pacific and you're applying it to a global model, then remember these are very region specific processes. The composition of the ecosystem and the processes in the Mediterranean versus the Atlantic versus the Indian versus the West Pacific versus the East Pacific, the subtropical gyres, upwelling regions, coastal regions, they would all be very different. So these are some things that cannot be avoided when we build these models. That's why using data to constrain the models and use all the approaches we have to validate and calibrate the models becomes very critical. And there are also ways to check the model formulations by model intercomparisons that I will come back to in a minute. Okay.